Welcome to the post-contest discussion of Codeforces round 1027 div 3. So what the first question says, you are given a string of 4 characters and each character is a digit and it represents a year. Now the question is, can the year, given year, can be represented like this, a plus b whole square format. Like for example, this given year is this, given year is this. Uh, can this be represented as a plus b whole square for some a b positive number or 0? So this can be represented as 0 plus 1. So for that I have to print a and value of a and b, and if not, then I have to print minus 1. So this is a simple brute force solution. Here you can see value of t is less than 10 to the power 4, and like since the year consists only 4 characters, so its maximum value cannot exceed 9999. So if we directly go to the code, so if you see, I take the input, then I converted this to an integer. Given expression is a string, so I converted this to an integer by using stoi function, string to integer function. Then like run a loop from 0 to root n and check if for any integer I between 0 to root n is I square is equal to n. If yes, then we got the answer. We can simply print 0 and I. If not, then like uh, any integer greater than root n will not be square of any integer greater than root n will always greater than n. So there is no chance that we'll get the integer which is we'll get an integer which is greater than root n. So I render loop till root n, and if I don't found a number, then I simply print minus 1. And if we see the complexity of this question, like t is 10 to the power 4, right? And like maximum value of n will be 9999. So square root of n approximately will be 100. So like big of t into n will be big of 10 to the power 6. So this will be accepted. Uh, uh, this will be accepted. So this is a simple brute force solution. Okay. Now let's go to the next question. So in this question, we are a binary string. We are given a binary string. Binary string only consists of zeros and one, and a pair of indices called good if like uh, I and n minus I plus 1 is equal, like uh, this pair of indices is called good if s of I is equal s of n minus I plus 1. Okay, this is the definition of a mm, good pair indices. Now here given some example for this binary string. S1 and S6 is not a good pair. Similarly, S2 and S5 is not a good pair, but S3 and S4, these two are equal, so this is a good pair. Now the question is, uh, 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 this character Vlad loves palindrome, but not too much. So he want to rearrange some character of the string so that there are exactly k good pairs. If the string is in palindrome, then there will be like exactly n by 2 good pairs, but I need only k, on exact k good pair. Okay, and uh, rearrange some character. There are no limit for like I can rearrange character infinite number of times. So like I don't need to minimize the number of rearrangement or etc. So simply, if you like reconsider the question as a you are given some number of one and number of zero. Say this is one and this is equal zero. Okay. Now can we construct a string such that exact k pairs are k pairs are good from these numbers. So how can we do that? Uh, Suppose n is given, this is given. So there are no like odd this. So if we iterate while while k is not equal 0, if we have more number of 1, then we can use 1 for a pair, right? You can use 0, but it will be better for us to use 1. I will tell you later why. So we will use 2 1 to make a pair. So number of ones will be decreases by 2, else number of zeros will be decreases by 2. We will use 0. Okay, and for every case one pair is done, right? So value of k will be increases decreases by 1. Okay, now the case is now the condition is like we are not checking we have enough one to you like we have uh, more than two one more than two one or more than two zero, like we are subtracting this, right? So uh, like after this while loop there might be a case where like number of remaining one will be a negative number, or remaining zero will also be a negative number. So now I need to check a case if one is less than zero or zero is less than zero. If yes, then the answer will be no. Or let's suppose a case where like a given string is this. Given string is this, so number of 0 will be 4 and number of 1 will be 3. And we need to make exactly two good two good pair in the uh, wait, uh, two like two good pairs. Okay, so clearly uh, 5 6 7 is this into 5. So since a number of zeros is greater than number of one, so we will first use two zeros, then this will be become 3. Now since both are equal, we can use any one. Let's suppose I am again using 0. Now since value of k will be now 0, right? So we'll come out of the loop. Now remaining one will be we have remaining we have three ones and one zero, right? And both are positive, so it will be no. But can we place uh, 1 0 and 3 1 here in such a way it will not create a good pair? Like there will be four cases: 0 0 0 1 0 0 1 0 0 1 0 0 1 0 0 0. So for all cases, this pair is good. Again here, this and this is good. Here, this and this is good, and here these two are good. So we can't. Uh, if we see, if like remaining 0 minus 1, like absolute modulus of this greater than equal to 2, then we can't arrange this remaining numbers such that there will be no good pair. So another condition we will get if absolute value of 0 minus 1 greater than 2 greater than equal to 2, then answer will be no, otherwise yes. If we go through the code here, first take the input, then like count number of 1, then number of zeros will be n minus number of 1s. Then again, while k is like greater than 0, since k is decreasing by 1, so it will be ended up 0 before any negative number, so it came out of this loop. So I am, if number of 1 is more than number of zeros, then I am using 1 to make a pair, otherwise I am using 2 zeros to make a good pair. Okay, if like any of the uh, remaining number frequency of any of the remaining number is negative, then uh, answer will be no. Or if the absolute difference between the remaining numbers is greater than equal to 2, then again answer will be no, otherwise yes. So this is also a like simple kind of brute force solution. So is this clear, or anyone have any doubt? Okay, then Abhishek will discuss CN.
So we will discuss question number C. Question number C says, given an array A and n integers, it is sorted in non-decreasing order. That is, AI is less than or equal to A of I plus 1 for all I 1 to n. Means we are given an array and the array is already sorted. And what the question says, that at any point I, at if A of I plus I is less than A of I plus I, if A of I plus 1 is less than the next element, then the next element can be made a new array. So if the current element on adding 1 is still less than the next element, then the next element can be made a new array. So we are asked to find from this given array how many new arrays can be made. So this is what question it is. Question is on the current element, if we add 1 and it is less than the next element, then the next element can be made a new array. And we are asked to find the maximum number of new arrays that we can form from this array. So from this equation, what it is clear is that if on adding 1 to the current element, if it is less than the next element can be made a new array. So we will like to make this array in such a way that the difference between the two consecutive element is always greater than 1. If it is greater than 1, then on adding to the any element plus 1, it will always be less than the next element, and we will tell what is the total number of arrays. So let's say 1 2 3 4 5 and 6. So firstly we will always take the first element, so we take 1. Now when you move to 2, we found the difference, so 2 minus 1 is 1. So on adding 1 to 1, it will give 2, which is equal to the next element. So 2 cannot be made a new array, so 2 will merge with 1 and form only one array. But we are asked to find the many arrays, how many maximum arrays. So we will remove this 2. Now on coming to the 3, on adding 1 to 1, it becomes 2, which is less than 3. So 3 can be made a new array. So our array count will increase by 1 and the array count is 2. Now we will move on to the next element. So since we have already kept 3, we did not remove 3, so our previous element is now 3. So on adding 1 to 3, it becomes 4. So it becomes 4. 4 is equal to the next element, that is 4. So we can't keep 4, so we can keep 1, we can keep 3. Now on coming to the 5, what is the previous element? Previous element is 3, because we did not take 4. So on adding 1 to 3, it becomes 4, which is less than 5, so we can keep 5. So 1, 3 and 5 we can keep. On coming to the 6, on adding 1 to 5, it becomes 6, which is equal to the next element, that is 6. So we can't keep 6. So 1, 3 and 5 are the three arrays that we can make. So the answer is 3. So basically in this question what we are asked to do, we are asked to find the array, basically a array, number of elements in an array in which no two consecutive element has a difference of 1. Means there should be the difference of greater than 1. It can't be less than 1 because array is already sorted, so it will always be greater than 1. So we are asked to find the array, the size of the array, resulting array after deleting the elements, so that the difference between the any two consecutive element is greater than 1, which is a very standard problem. So I will show you the implementation. uh, uh, this is n is the size of the array. I have taken declared a vector, taken the vector as input. Now int answer is equals to 1. We will always take the first element. So and previous is the first. Since we have taken the first element, so for the next element, first element will act as the previous element, through on which we will check if the difference is 1 or not. So this previous is 0. Now we will traverse from the second element of the array from 1 to n I plus plus. If the current element minus previous element is greater than 1, then we can keep this v of I, we can keep this current element. So our answer increases and the previous element now becomes v of I. If it is not the case, we will not keep. If it is greater than 1, we will not do anything, we will skip. So at last the answer will be our answer. So what is the size of the element? So size of the array in which the no two consecutive element has a difference of 1. So this is what the question says. Now I hope this is clear. Yeah, we will talk on that. So moving on to the next question, question number D. So what the question says, that there is an infinite, there is a 10 to the power 9 cross 10 to the power 9 matrix. So let's suppose there is 10 to the power 9 cross 10 to the power 9 matrix with a cell at the intersection of ith row and bth column is AB. There are n monsters on the game field, with the ith monster located in the cell XI, YI. While the other cells are empty, no more than one monster can occupy a single cell. This is basically a question. We are given n monsters and the location of the nth monster in the matrix. So let's suppose the at 1 comma 1 there is one monster, at 1 comma 2 there is another monster, and at 2 comma 1 there is another monster. So there are total 3 monsters. And what we have to do, we will get one chance and we will select one rectangle, and in that rectangle all the monsters must lie in that rectangle, and the cost of removing all the monsters will be the number of cells in that rectangle. But we are given one liberty. What is that liberty? We can place any one of the monster to any cell exactly once. Here it is given, you can move one monster to any cell on the field that is not occupied by another monster at most once. So at most once we can place any of the monster to the any other cell, but the remaining n minus 1 monsters will remain at their places. So we will select one rectangle, and in that rectangle all the n monster must lie, and this number of cells in that rectangle will be our answer, and this answer should be minimum, as it is said that the minimum number of points. So what the intuition says, what I thought is, let's suppose I will remove this one, I will remove the monster which is at 1 comma 1, and I will make a rectangle out of the remaining n minus 1 monsters. And in remaining n minus 1 monsters I will make a rectangle, and if the number of cells in that rectangle is greater than n minus 1, what does it mean? It means there is empty cell in that rectangle, and in that empty cell I can put this one rectangle, one monster. Similarly I will do for this. I will remove 1 comma 2 monsters, and I will make a rectangle of 1 comma 1 and 2 comma 1, and I will check the size of the rectangle. If the size of the rectangle is greater than n minus 1, then there must be at least one empty cell. So I will put this monster at 1 comma 2 inside that empty cell. If there is no empty cell, if there is no empty cell, then the rectangle that is made by the remaining n minus 1 points will either increase by its length, either increase its length by 1 or its breadth by 1. I'm explaining. Let's suppose this is the matrix. Let's suppose here is one monster, here is one monster, and let's suppose any other position, here is one monster. So what I will do, I will first iterate from all the monsters. I will choose this monster and I will remove this monster. I will not consider this monster, and the remaining n minus 1, that is remaining two monster, I will consider, and I will select the rectangle which covers both the monsters. So this is the rectangle which, sorry, this is the rectangle, this is the four cell rectangle which, this is the four cell rectangle which incurs all the remaining n minus 1 monsters. So I will calculate the number of cell in this rectangle. So number of cell is 1 2 3 4, but the number of monsters left is only 2. So there are two empty cells. As you can see, there are two empty cells, so we can put this one monster in either of the empty cell. So one answer is 4. If we keep this monster left out, our answer is 4. Now we will keep this monster left out, we will uncover this and this monster. So the maximum, so the rectangle will be from 2 to 5, will be row from 2 to 5 and column from 2 to 5 again. This monster and this, I want to include this monster and this monster. So the row will be from 2 to 5 and the column will also be from 2 to 5. So what will be the total number of cells? From 2 to 5, 5 minus 2 plus 1, so 4, 1 2 3 4 length, and in column also 1 2 3 4 columns. So 4 cross 4 is 16 cells. So we have 16 cells. So in 16 cells, this monster already lies in that cell, but if we have only two monster, but we have 16 cells, so we can keep this extra monster inside this cell. So this could be our answer. So in first case our cell was 4, in second case our cell was 16, and now in the third case I will left this monster out and I will enclose these two monsters. So the minimum rectangle would be from 2 to 3, length would be from 2 to 3, and breadth will be, sorry, breadth will be from 2 to 3 and length will be from 2 3 4, 2 3 4. So breadth will be 3 and length will be 2. So 2 into 3 is 6. So there are 6 cells. We required only 2 cells, 4 cells are left out, so this one monsters can fit into it. So how we are calculating the, how we are calculating the number of cells? So let's suppose the row number, let's suppose if there is minimum row, maximum row, minimum column and maximum column. We are given the coordinates of the monster, so we will remove one monster out because we can keep this monster inside the any cell. So we will keep this monster out, and in the remaining monster, in the remaining monsters coordinates, we will find the minimum row, minimum column and maximum column, and the number of cells will come out. Cells will be minimum row, sorry, will be maximum row minus minimum row plus 1 into maximum column minus minimum column plus 1. So this is the number of cells, or basically area of the rectangle which encloses the remaining n minus 1 monster. How I got this formula? This is quite simple observation. So let's suppose if for this and this monster, what is the minimum row? Minimum row is 2, and maximum row is 3. What is the minimum column? Minimum column is 2 and maximum column is 5. So 5 minus 2 plus 1 is 4. 5 minus 2, 3 plus 1 is 4, and in case of row, 3 minus 2 plus 1 is 2. So we can say that we can see 2 is the length and 4 is the breadth. 1 2 3 and 4 is the breadth. So this is how we can calculate the area. So we will do a greedy approach. We will first pick one monster, we will left it out, and the remaining n minus 1 monster we will calculate the area. And if we will check if in the area there is at least one empty cell, we can put this monster or not. Then the answer will be that area also. Now check one case. If this is the scenario, star here and here also monster, and I will remove this monster, and I will calculate the area for the remaining monster. So for the remaining monster I will get a area of 4. So the remaining monster is also 4. There is no empty cells. You can see there is no empty cells. So in this case what I can do is I can either increase the length, that I can occupy this, or I can occupy this. So in this case the length and breadth both are same, so it is, so we can either extend the length by 2 or breadth by 2 and put the remaining monster here. But let's suppose the case is something different. Let's suppose we are given here star and here star. This is the case. Now the length is 2 and breadth is 3. Now the length is 2 and the now the length is 3 and the breadth is 2. So for this one monster, what will be optimal? To increase one row or this one column? If we increase one column, we will get only 2 extra cells, and if we increase this column, we will get 3 extra cells. So it is always better to extend towards the length or breadth, whichever is minimum. So this is the logic of this question. Basically, what is the logic? We will traverse from each every monster. We will remove that monster, and for the remaining monster, we will calculate from this formula the number of cells. And in that number of cells, if there is at least one empty cell, then we can keep this monster inside it. If it is not, then we will check if the length is minimum, or this is the length. This is length, and this is breadth. So from both of these, what will be the minimum? We will extend that. We have seen already this is 3. So if we will extend the row, then we will wasting 2 spaces. We will keep one here and we will be wasting 2 spaces. But if we will extend in horizontal, we will only be a space uh, wasting 1 space. So this is the whole solution. I will show by code. It will be better. So let's suppose this is the n number of monster. I have kept one multi-set L and R. Well, L will be placing the x coordinate and R will be placing the y coordinate. Vector of pair will be storing the x and y coordinates. As I have to use this, so I have again storing it in vector. So int xy, I have taken input, pushed into the vector, and x coordinate I am pushing into the L multiset, and y vector I am pushing into the y. If n is already 1, then answer is simply 1, because that one cell is enough to uh, kill the monster. Now I have said answer is maximum possible. I have kept the answer maximum possible. Now I will iterate from 0 to 1. I will iterate from all the monster, and I will leave that monster. So I from 0. Then I will calculate the coordinate of the monster which I am leaving. So I am deleting that monster. I am deleting the x coordinate from multiset which is storing x, and I am deleting the y coordinate from the multiset which is storing y. So from till this I have deleted the ith monster. Now ith monster is not in the picture. So for the remaining n minus 1 monster, I am calculating the number of cells that is required. So how the number of cells is required? The minimum row is first element of the L set. Maximum row is last element of the L set. Minimum column is the first element of the R set, and maximum column is the last element of the R set. So out of this, I am calculating the area required to accommodate the remaining n minus 1 monster. So if area is greater than n minus 1, means there is empty cell. So if there is empty cell, I don't require any extra cell for this ith monster. So answer is minimum of answer comma area. If it is not the case, so answer is minimum of answer area plus I need one extra row or column. So whichever is minimum, either row is minimum or column is minimum. This is coming from this formula only. Either row is minimum or column is minimum. Whichever is minimum, I will extend it into the area. And again, since I have deleted this monster, so I have put this monster again back into the set. So again, for I equal to 1, I will remove the 1th monster, check for the remaining n minus 1 monster, and again put it back into the set. So after all checking all the conditions, the answer that will be the minimum, I am printing that. So basically I am removing all the monsters, and for the remaining n minus 1 monsters, I am calculating the number of cells required. If number of cells required is greater than n minus 1, means there is already an empty cell, so we don't require any extra cell for the monster that we have left out. But if it is exactly n minus 1, then we required some space for this monster. So either you can extend the row or you can extend the column, whichever is minimum I will extend that. So this is the logic of this question. I hope I'm clear. This is it for the solution.
Okay, am I audible?
Yes, yes.
So I'll be discussing question number E. Okay, I hope my screen is visible. So let's start. So what basically this question number E is stating is that for any point in a tree that will be given to you with a set of values, each node will be assigned a value with it. So there will be a path, right, for the root from that vertex to the root. You will do an alternate summation, kind of like, for example, let's take 3 into consideration. We will be doing 2 minus 5 plus 4, something like that, okay? But for a path, for example, let's say between 4 and 2, it will be like 6 minus 2 plus 5, kind of alternate in an alternative fashion, okay? First addition or the vertex itself, after that subtraction, after the addition again. So there, how many paths are there, such paths from here to here? One is 4 to 4 to 4, okay? Yeah, you can, it's not necessary for you to go to the root itself. You can stop here as well, or any other vertex that is along the path of the root. So from 4 to 4, 4 to 3, 4 to 2, 4 to 1, right? Now what you are asked is, for each vertex, for each of the vertex, you have to find, or node, you have to find the maximum value that you can have, right? For example, let's say how many values this guy can have. That is 6 minus 2 plus 5, that is 9, minus 4, which is 5, and then there is 6 minus 2 plus 5, that is 9, then 6 minus 2, 4, then 6. So among this, the maximum value is 9. So we'll take the path from 4 to 2. So similarly, you have to find for all of them. Now, one approach might be to calculate for each of the vertices individually. Like, we can just kind of do the alternating fashion and check it for each and every node along the path, but that will of course give you time limit exceeded. As the constraints are quite high, you need a big open solution. So now how can we do that? We actually don't need to calculate each and every one individually, each and every path. What you can do here is that, see, here is 4, right? And the 4 will be subtracted here. So if we take the value of 4, this will be minus 4 for this value and this value, right? Sorry, minus 4 for this value and this value, and a plus 4 for this value and this value, right? So what we can do is that, what we can see is that it is, since it is in an alternating fashion, nodes values for the future nodes, so we can store it and create two separate values. One will be 4 for this node and this node, and one will be minus 4 for this node and this node. So of course we want the maximum, so we'll not consider minus 4, right? So we'll consider 0, so that will be 4 comma 0, and similarly we'll keep on doing this for each and every node. I've drawn a graph for that. So see, it had a value of 4, so now it can go here. So one value will be 0 because minus 4, so we'll not consider minus 4, right? We don't want negative value. So because see, the summation from top to until this point was minus 4. So irrespective of whether we consider the future values or not, it will always be negative only. So we'll not consider it at all only, and we'll consider it to 0. After that, we'll look at 2. At 2, the value is 5. So since 2 is in opposite sign with this guy, so we'll consider 0 1. Okay. So what is 2? 0 plus 5? It's 5. So we'll get the maximum value of 5. For here, it will be 4 only because it's the root itself. And then we'll consider this guy. And for this guy, we'll consider the right one. Because for it, this and this have the same phase. They are in this phase with each other. Both of them will be positive. So here again it is 0. Why 0? because this value is 5, so 4 minus 5 is minus 1, so 0. And this guy will be added 5, so 5 comma 0. And 5 comma 0 we have, and the value is 2. Since we will be adding value here only, so the maximum value for subtracting value for this guy, so we'll be having a maximum value of 3, right? Which note this one is? Oh, sorry. We will be adding a value to the 0th node. It's an alternating fashion, right? So first we considered this value, then this value, and then again this value. Now again we'll considering the third value is 3 here, and 3, this value has a 6 if I'm not wrong. It is 6, so we'll be adding 6. So we get the 9, and thus we got the result. And for this guy we'll be considering it to minus 4, so it's pointless to consider this node, so we can just take 7. So we get the maximum value of 45297. And this will be the basic intuition. For this question, we will just be having two values, one in one phase and in the other phase, and we'll just keep a track of it, and we'll just keep on adding it for each and every node, and we'll store it and just output it. So this is where I've created the graph or the tree, whatever we call it, and then we're storing those two, and then we're doing a DFS. So basically, I'm just marking it true, and as I've already told you, if it is in positive phase, just basically current. If it is true, it means that it is in phase with the root. Basically, if the root is positive, it is also positive. If the root is positive, it is negative. Sorry, it is if it is positive, root is negative for the else one. So for the positive part, we will be adding this node, and for the negative, we will be subtracting it, and the opposite in the else part. And then of course, if for example in any case it goes below 0, then we'll be making it 0 itself only, because there's no point of considering this node in future. And then we'll consider these values, store it, and then again DFS, since we don't want to visit the parent node again obviously, so we'll just use the not visited here, and then we'll output the value. I hope my implementation and logic is clear, or are there any doubts? Is there some part which you want me to explain again or dry run, or is it clear? Okay, then.
Am I audible? Okay. So in this problem, we are given two numbers x and y, and we have to make both of them equal by performing some operations. And also, we are given a integer k and oh, yeah, integer k, and we have to either divide number x or multiply number x by a number a such that it becomes equals to y. So we have to perform some number of operations to make both of them equal, and we have to minimize the number of operations. So in order to minimize the number of operations, we have to apply some dynamic programming idea or whatever. Let's check out. So we are given two numbers, x and y. So and k, integer k, we have to make x equal y. So in order to make x equal y, what we have to do? We can, I guess, either divide or multiply x to some number. So we have to either divide x or multiply x to some number to make it equal to y, and we have to do certain number of operations to make it equal to y, and we have to minimize the number of operations. So in order to make x equals to y, what we have to do, first of all, x and y will have something common in both of them. So what is the number that they will have common in both of them? That is simply equals to, I guess, gcd of x comma y. So we can find it the GCD of x comma y in logarithm of n time. It's using the standard template library, and after we find the GCD, we finally have got the number which is common in both x and y, right? And now the number which is in x but not in y, the number which is in y but not in x, what it will be? So it will be x by GCD of x comma y. This is the number. This will be the number that will be the number that is in x but not in y. So we have to divide, let this number be a, we have to divide x by a. We have to divide x by a because that number is not in y. That number is not in y means it's, in order to make it equals to y, we have to divide x by y. So we will divide x by a. And similarly, another number which is there in y but not in x, that is simply, let that number be. So b will be equals to what? Y upon, I guess, GCD of x comma y. So we, this is the number which is common in y but not in x. So in order to make x equals to y, we have to multiply x by a. Fine. So we cannot directly divide and multiply by a or b here because we have to make sure that a comma b lies in the range of k, right? We have to divide and multiply in such a way that we have to also ensure that. So in order to do all of these things, first of all, finding GCDs in logarithmic time, okay. And after that, we have to minimize the operations, right? Simply we have to we have two numbers. Now the problem is just reduced into two numbers, A and B. We have to make this A and B, like produce this A and B using some multiples which are from 1 to k, somewhat like this. So we have to reduce them in such a way that they are expressed in terms of product of numbers from 1 to k, and the number of numbers are should also be minimized. So if we understand now what is happening, this problem can be solved using dynamic programming. So a and b are separate here. A and b are separate here, like we have to first of all divide x by a and then multiply x by b. So for dividing x by a should be expressed in terms of some product of some numbers. Let's suppose it's a1 into a2 into a3 or so on, such that all the numbers a1 a2 such that all the numbers a1 a2 a3, all of them are, I mean, like greater than equals to 1. Yeah. So in such a way that this, and then we separately will divide x by a1 and then x by a2 and x by a3 and so on. So in order to find this product or minimize the number of numbers in the product, we can apply dynamic programming ideas. And similarly for b can also be expressed as some sort of like that, and so on. So we have to, and then we'll multiply separately by b1 and x by b1 and b2 and b3 and so on. We'll multiply them separately. So after doing all these operations, it will become equals to x. Now the problem here is we have to minimize the number of numbers expressed in the product. Like suppose here in this way, here like some capital X numbers are there up to ax, must be x. Yeah, here up to some by. Then the answer will be
x plus y, and we have to, I mean, like, minimize x and y. So in order to do this, we will apply dynamic programming. Now the idea is, let's understand, we can pre-compute all the devices from of all the devices of the numbers from 1 to 10 to the power 6 in logarithm of n time. And after pre-computing the devices, we will apply the dynamic programming idea. And we can even apply the recursive dynamic programming ideas to solve this. So since the range is of x comma y is given 1 to 10 to the power 6, we can pre-compute devices in n log n time. After that, we can apply dynamic programming. So let's see how I have pre-computed the devices. So this is the accept solution. Yeah, this is the step where I am kind of pre-computing the devices. So this is a simple harmonic series. So it's going to take 1a6 log 1a6. So I have pre-computed the divisor of each and every number. So after pre-computing, the now the idea is completely about how you think about the recursive DP. So after pre-computing the divisors, we know the divisor of each and every number now. So we take the input, and if both of them are equal, then simply the answer will be 0. So this is simply I have added a edge case. And after that, now it is about, like, yeah, let's get into this. So this is the common number, like common both of the x and y. So I have taken the GCD to find out the common number. And so what is this is simply the number which is in x but not in y. So this is another number which is in y but not in x. And simply I have applied the dynamic programming idea to kind of, this is simple, like I have applied recursive dynamic programming idea. So simply I have to express in this form, right? So here I have to minimize the numbers in the product, both of the cases. So in order to do it, I will apply dynamic programming ideas. And after that, after I minimize both x and y, I will simply add. So that's what I have done. I have applied the dynamic programming, recursive dynamic programming here, which I have implemented. I will explain that later. So after doing this, we simply, if the answer does not exist, then it will return negative one. So I have checked it, and if both of them sum up, then the answer will be that. So that now the recursive dynamic programming idea is, let's understand the recursive DP here. So the recursive DP, let's take the DP of I is, let's understand the state of the dynamic programming here. uh, Minimum terms I can be broken, I can be factorized, or whatever, expressed in term of product of all of numbers that are less than equal to k. This is what is the our dynamic programming state. So minimum terms I can be expressed in term of product of numbers that are less than or equals to k. So after, now how do we find the how do we find this what a solution for this? So we will go through all the divisors of I. Suppose all the divisors are like, somewhat like divisors are uh, like, suppose some of the one of the divisor is suppose capital A. So dp of I will be minimum of dp of I and 1 plus dp of I upon E. Simply we will recursively apply this relation to find the solution. So it can also be solved using iterative DP. It is up to you what you choose. and the time complexity is gonna be like closely to O of n, because we have pre-computed the divisors, and rest of the DP calculation, like the sum of all divisors will also be always less than 1e8. So it is gonna be solved in around like O of 18, 1e18, as it is given in the constraints. So that is what I have done. Like I have what I have written, that's what I have done. I've gone through all the divisors, and we should also make sure that the divisor does not exceed k, because then it will violate our condition. So that's it. That's what I have done. Like I've recursively used the memorization. You can also use iterative. So if this is clear, then let's end. Like, is this, yeah? Let's go to problem G. In problem G, we are given that we are given an empty array, and we have to make a give, arrays. We have to make an array by adding integers to the left of the array or the right of the array, and then once the adjacent pair of elements are same, we have to replace them by sum until there is no adjacent pair of elements same. So this is the simple operation. We have to add an element to the left and right, and after two adjacent elements are same, we'll remove them and add the sum, and we'll simply keep on doing until we don't have two consecutive elements same. That is what is mentioned here. So, and then we have to perform k operations. Okay. So we are simply this, we are now asked in the reverse manner that we are given an array. Can that array be created using the operations, exactly k operations? So we should start with an empty array and try to make the array given in the question, right? Try to make the array given here in k operations, exactly k operations, right? So we should not make exceed k operations. We should, it should be less than, we should be exactly k operations. So we'll simply add element to the left or right, and then simply we'll try to make the array given to us. So, and this is really important, like I mean, like no adjacent elements will be same. It's already mentioned in the question, so we don't need to check the condition again. So yeah, suppose let's take one example. So since we have to append the elements, suppose we have to make 2 1 4. In suppose we can make, in best case, how many operations it will take? At least it will take 3 operations, right? Because there are 3 elements. We'll start with empty, we'll add 2, and then we'll add 1, and we'll add 4. Best case it will take n operations, and that's why the number of operations here, k is always greater than equals to n, and already that is simple. And now the point is, we have to now think in a way such that break the problem into a single element. How many operations maximum can be used to make an element? That is really important. Suppose if we start with, suppose we add two elements, what is going to happen? Like they are simply, when we are adding two same elements, it's simply they are getting multiplied by 2, right? They are just simply multiplied by 2 here, and you can simply see some pattern that they are exponential, like that is exponential growth is there here. So something related to logarithm, something related to bit masking is really clear, because when we add two same numbers, they are multiplied by twice. So that is gonna, this is leading us to some exponential growth. So in order to make a number, suppose it is somewhat in the terms of 2 to the power something. So 2 to the power n, suppose we have some number randomly, we have to make this number using some number of operations. We can make it using one operation by directly pushing, or how many operations in the worst case we can, best maximum number of operations we can use, like we will simply push first one and then another one. This will become, since two adjacent elements are same, it will become a 2. And after that, after we'll push again one, we will push one again, So after this we will push again one. After this we will push again one. This will become what? We will end up here. We will end up in 2 2. This will again become 4. And so on the operation will go on. We can keep on pushing ones. So if a number is in the form of 2 to the power n, then the number can be made in 1 to operations will go can go from 1 to 2 to the power n, right? If this part is, I want to know whether this part is clear, because this is the main part. Like when the number is in the form of 2, some power of 2, it would take us exactly 2 to the power n operations to make. Maximum number of operations that can be used is 2 to the power n to make it. From 1 to 2 to the power n, you can use any number of operations to make it. So if this part is clear, then let's understand. Every now, sorry, yeah. Now every some suppose that some number is not in the form of 2 to the power m. Suppose it is somewhat a number. Let's see, it's the number is b, which is not in the form of 2 to the power n, but still it can be expressed as 2 to the power n into some constant. Suppose it is c. Every number can be expressed in the some power of 2 and some constant. Obviously, c will be odd. C will be odd. So now we are going out of the box here. Like we are now considering the other cases when the number is not in the form of 2 to the power n. So it will be somewhat in the form of 2 to the power n into c, where c is some odd number. So such a number can also be made. Such a number can also be made in 1 to 2 to the power n operations, because let's understand why. Such a number can also be made in 1 to 2 to the power n operations, because now this time we will start with c. Suppose we'll push one c. First of all, it is empty. We pushed one c, and then it will remain c. We push another c, it will become 2c, and after that, since there are two c's, it will be 2 times of c, and again after that you will push another c. So 2c, c, another c again. This will lead to 4c. Like I'm directly skipping some steps. So now you can understand, instead of one, this time you're pushing c, and everything is same. This can also be made in 2 to the power 1 to 2 to the power n operations. So every number can be made using these many operations. Now this is like the most important part to understand this problem. So if this part is clear, then the problem is like now really easy. Like we'll calculate the maximum number of operations that can be used, and if the k is less than equals to the maximum number of operations, then it is possible, else it is not possible. But there are some few edge cases here. Like the point here is, suppose we have to make some sequence of numbers like 1 to 4. We can either start from 2 and go to and go building from left to right, or we can start from ending and start from 4 and go to right to left. There are two ways of making this array, and simply uh, from which element we have to start decides the maximum operations, because we have to consider the previous element also, right? Because the sum can be both this. If both the elements become same, then we have to add them. So we have to consider all those edge cases here. So suppose we are starting from left to right to make this somewhat like 214. So we'll start from by pushing one here, one, and you can understand like once you, I mean, like if the number, suppose we have
Pranav,
done until here.
Pranav, that part which is to the power n into c. Can you explain
Mhm.
it by an example? I did not
Yes, yes.
understand. Sir.
Okay. This is like the most important part. So suppose we have 10. Let's take an example of 10. Right. How can 10 be written as 25? This is clear, right? Simple. So now you want to make 10. How many maximum operations we can use? First is the maximum operations is means we'll start by pushing 5. We'll push 5 into the array. Okay, now we'll push another 5. Okay, I pushed 5, I pushed 5. Okay, now both the elements have become same, so it will become 10 as mentioned in the question. So how many operations it took us to make it? We have pushed two elements, right? So the number of operations taken is how much? 2. So now we
Yes.
can generalize this fact, right? It will take 2 to the power n. Instead of 1, we are pushing 5. That's it. C.
Okay.
Like, is this clear? Like, you can do
Yeah,
it
yeah.
yourself. Like, yeah, this is the fact. Like, it can be. I mean, like, it's gonna. It's this number will also take 2 to the power n operations at maximum to make it. So now there are a lot of cases here, but we'll consider everything. Suppose we have made completed the array. Suppose whatever the array may be, we have completed up to some index. Suppose we have completed up to ak, means we have when somewhat somehow we have performed operations, and we have converted the empty array into this form, and we have to make some element b here. So if ak is greater than b, then there is like greater than b, obviously it cannot be equal. Then we can simply make by using whatever number of operations. This will not matter to us because the previous element is greater. So we'll start some with some elemental element and then keep on adding. It will not impact because the previous element is greater than whatever we do. Those two consecutive elements cannot be same. Like ak will not interrupt our addition process here. So this is the ideal case. But when what happens when somewhat like ak is less than b, then this thing like makes us a bit difficult things. So suppose let's understand with with some example. Suppose we have to make 2 and 4, right? We have to make this array 2 comma 4. We are starting out with nothing. So simply we will push. First of all, somehow we made 1. Okay, we have made 1, and but now we have to make 4. So we let's start with the elemental thing. Like we push 1, whatever I talked. Again another one will push. This will become 2 2. So this now becomes 4, which is not which is now making things complicated for us because this is not what we want. We don't want to disturb the previously made elements because after the entire process can be ruined by this. So this means we cannot push. Now we cannot push the smaller I mean like very elemental elements here. We have to somewhat pick a big element here. Like to make suppose we already have 2, then we have to make a 4. Means the only thing here is we have to push 4. There is no other combination left because whatever you push, that is going to disturb the 2. Like I want to know this is clear or not, because this is like we don't want to disturb the previous elements that we have already created, and we have to focus on the current element. So now, when is our element going to be disturbed? It will only be disturbed when the previous element ak or whatever is less than the our current element b, and it should be less than, and the both must be divisible. Like b must be divisible to ak, and the value b by ak must be some power of 2. Like you can understand this fact by yourself. Like it must be a power of 2, otherwise it there will be no interruption. Because let's take with some other more examples. Suppose we have somewhat a 5, or you can take some element, some other things. Suppose you have 5, you have to make this array. Okay, we somehow made up to 5, and we have to make 10 also. So if we push 5, This is like again, this will become 10 because this is now again violating our condition. It's because 10 by 5 is equals to 2, which is a power of 2. So this is simply violating the conditions. In that case, we have to directly push the a larger number. Like we can only push the value which is larger than the previous element. Suppose we have 5, then we have to push 10. There is no other way. We have to push the larger values only. So there are two cases here. Suppose we have, let's I mean like this means we can only make the 2 to the power difference between the difference. Operations will go from 1 to 2 raised to the power like difference, like this law, you can take it whatever you can take, somewhat like a value, like you can understand the pattern that the difference between the powers has to be considered in this case. And after considering this, simply the maximum operations can be calculated. uh, the two cases of starting from the 1 and going to n, and starting from n and going to 1, like the reverse case from left to right and right to left building. We'll consider both the cases and find the maximum operations. Okay, fine. This is the these are the only two cases we consider, but there is another case. Like suppose we want to make some array like a1 to a2 a3, somewhat like array, so on a4. We can start, first of all we can start from a2 and go up till a4. This is one case. This we can start from a2 this time and go up till, like, the starting element is really crucial here. We have to consider all the starting cases, and then we will build from left prefix and the right suffix. So we'll consider each and every element that we can start, and then simply we consider all the cases of possible building, and we'll take all these cases. Like here only four cases are there because I've taken an array to be made having only four elements. So we'll consider all these cases and find the maximum number of operations that can be used to make the array. And if the k is less than or equals to that maximum, then the answer is possible. That is what we need to do. Like for doing this, we can use the prefix and suffix technique, like because the connections are related in the prefix and suffix. So we'll pre-compute every prefix and suffix, uh, and then we'll simply solve, consider all these n cases and find the maximum. Like this is like really complicated, but at least something you understood. I feel. So now that the logic is clear, like we'll consider every case of building the array, and we'll try to find out the maximum number of operations that can be used. And if that maximum number of operations is less than equals to k, then means the answer will be yes. So we'll consider every possibility, like which element we are taking as starting. So since we can use, so in order to do this, suppose we pushed out some element, we starting out from element ai, let's see. So there will be some prefix here from up to A2, and we start off building in this way. Like we'll build the left part and then right part, or right part and left part. We will, like, we know this answer. Like we have already pre-computed this prefix and suffix part, so we'll directly know whatever it's going to take. And we also know the operations that we can maximum performed in this left prefix and the right suffix. And then we also know the AI. So we just combine all of them and try to find the maximum operations. So that's it. So let's go to the implementation then. Like this is what actually we need to do. But there is another edge case here. But I'll discuss it also. Like the edge case already I've explained, the difference of power that always does not do the job. So suppose the previous element was 2 to the power n, n minus 1, n minus 2. Suppose now we need to add, suppose 2 to the power n. I'm randomly taking some element. So the best way of making this array is, we already have this, and we add, first of all we'll add 2 to the power n minus 1. I've like, we have pushed it to the array, and then after this we will add here another 2 to the power n minus 1. We'll create that, which will cost us at max, which will cost, total it will take somewhat like 2 to the power n minus 1 plus 1. This is the best case scenario. Like, I've thought a lot and came to this greedy idea that whenever I have to make somewhat like this pattern of numbers, this is the only way to make, best way to make. First of all, we'll push the 2 to the power n minus 1, and then the rest of the part can be made, which will already, we have discussed this part. This is the only edge case, and that's it. Let's go to the implementation. Okay, was yeah. Okay. So first of all, I've taken nk and array. I've taken input, and then I have used a function to calculate, because the prefix and suffix have to be calculated two times here. So for both of them, I have simply written out one function, and this is the I've calculated the power of two, like 2 to the power n into b, that power, and I've already stored it. And after that, now I have to calculate the prefix, right? I will take the prefix sum for that operations. So before that, like I've discussed this edge cases, right? When the previous element is less, previous element is divisible, whatever the edge cases are there, and considering all those edge cases, we have added the optimal answer. And after that, I have taken the prefix sum of the answer, like, because see, I have explained this, right? We need the prefix and suffix. We need to pre-compute the prefix and suffix, so we don't have that much time. We have to use prefix and suffix sums here, like that's why it's operations prefix sum. And then I've just calculated the prefix and suffix using functions. You can do whatever you want. And then I have considered this one, like I have considered starting from each and every element, and then try to find the answer possible, maximum answer possible for them. So first of all, we'll build that element that will cost us 2 to the power whatever n times n operations at max. And then this is for the prefix, and this is for the suffix. Total operations maximum it can be costed. And then I've already also made it maximum. And then if the maximum is greater than k, the answer will be obviously possible, because maximum operations is greater than k means that we can somehow make it some adjustments to reduce operations, so we can always build that array. So I hope this was clear.